Philadelphia, we are back at the Keswick Theater. StarTalk Live! And now, we're going to talk about black holes for the next hour and a half. You got it. Black holes. And I have some expertise in black holes, but not enough to fill the length of this show.
Okay.
So we combed the landscape for my colleagues who spend their lives thinking about black holes.
Yes.
We found one of them at Princeton University, not even that far up the street as far as distances go. Welcome to the stage, Jenny Greene, professor of astrophysics. Jenny, there she goes. She's otherwise known as the black hole hunter. So you study supermassive black holes and how to find them and where they're located in the universe. So you're a black hole hunter. And you also, she is faculty director of the Prison Teaching Initiative at Princeton.
Wow.
Princeton has a program where faculty go to the prison and teach. You teach algebra, is that correct?
Correct.
And so that the prisoners can come out with some kind of a degree and reduce the recidivism.
Yes!
We salute you. Next, another black hole expert. One of our favorites, she's a regular on StarTalk, really, and she is professor of physics and astronomy at Barnard and Columbia University. Janna Levin. Janna, come on out. Janna. So, just so we understand the context here, we have Janna Levin, who approaches this problem of black holes as a physicist, and she's interested in cosmology, space-time continuum, and the like. Whereas we otherwise are searching for actual black holes in the actual universe, and so these are two sides of the same coin that we're going to explore this evening.
Nice.
So let's do this. All right. So, Janna.
Hey.
Hey, how you doing? All right. There was news yesterday, that there was a report that people, colleagues of ours, have images of where jets, these plumes of gas, spewing out from the centers of galaxies, that we have images of where that connects down to a black hole at the center. Could you please comment on that?
Yeah, so the irony is that black holes, which are by definition the darkest phenomena conceivable in the universe, are the brightest beacons as well, because they figure out a way how to access all the energy and light and power around them. So they power these jets. We can see the jets at great distances. Sometimes they're 1 million light years across. They're enormous. They're bigger than the entire galaxies. But what yesterday's result was about was seeing it attach itself threaded through the black hole. So we can see it so close to the event horizon of the black hole that it really validates the idea that it's the black hole that's doing this.
Okay, it just occurred to me. I know you're all fans of science. You wouldn't be here otherwise. But let's make sure we're on the same page. Okay? So tell us what a black hole is.
Right.
Oh, that's a good thing.
Look, I was not pointing to you, Chuck.
Woo!
Chuck,
I didn't want to ask myself. I was just like, oh, when are they going to get to this part?
You should always ask.
Exactly.
Always ask.
Yeah, so Jenny, tell us. Just give us the basics of a black hole.
So a black hole is an object with so much mass in such a small space that not even light can escape its gravitational pull.
So is it fair to say that the escape velocity, which is the speed necessary to leave an object forever, on Earth, I memorized all these, on Earth it's 7 miles per second.
Wow.
So Chuck, that old saying that your grandmother said, what goes up must come down?
Right. Not true.
Not true.
My grandmother was dumb as hell.
So if you could throw... She just didn't have intro physics.
This
Chuck.
is true, right.
So if you can throw faster than 7 miles per second, it will leave Earth and never come back to Earth. Okay, and so the sun has an even higher escape velocity, as you might expect. So a black hole, the escape velocity, is it fair to say it's greater than the speed of light?
Even going at the speed of light, you could not escape the gravitational pull of a black hole.
So I'm on Earth, I toss something up and it comes back. If I take a beam of light on the black hole and turn on the flashlight, what happens to the beam of light?
Oh, I love that one. You can actually get it to hang there forever.
Light with hang time.
So the region that Jenny is talking about, beyond which not even light can escape, is known as the event horizon. And it's just a demarcation line. There's nothing
Isn't that a nice
there.
poetic term for something that'll just kill you?
Yes.
No, the event horizon. You got to say it.
It sounds innocent.
You have to say it's smoky light.
Yeah.
But if you release a little pulse of light exactly at the event horizon, it will try to race outward at the speed of light, but you can think of the event horizon as a region where space-time is falling inward like a waterfall at the speed of light, and so it just sits there.
Oh, look at that. Oh my God, you just described my marriage.
Good thing this isn't going to be on TV or anything.
Don't worry, she's here.
So Janna, you wrote a book called The Black Hole Survival Guide,
Yeah.
which is a little scary because you should not come close enough to a black hole
Yeah.
to ever have to think about surviving it.
Yeah.
Is what I'm thinking.
Yeah, spoiler alert, it doesn't end well.
Yeah. Okay. So you said that black holes are nothing.
Yeah.
They are no thing.
Yeah. They're not a thing.
They're not a thing.
They're not a thing.
Why are we here?
You can think of a black hole in some sense as a place. It's a place, it's a region in space, as you said, beyond which not even light can escape. But that region, that event horizon, is left like an archaeological record on the space-time. The thing that formed the black hole, maybe it's a collapsing star, it can no more sit at the event horizon than it can race outward at the speed of light. So once it collapses under its own weight and it forms this region where everything goes dark, it is forced to continue to collapse and leave behind an empty space with nothing in it.
It's a prisoner of itself.
Yeah.
Ooh.
Oh.
So its gravity created its own cage, in a sense.
Yeah, and when the star forms it is forced to disappear as well down the black hole. The black hole, it's like dispenses with the star. So whatever made it is gone. So if you go up to that edge of the event horizon, it's as undramatic as stepping into the shadow of a tree. There's nothing there.
So when people think of a black hole as a solid object, clearly it's not.
It is not.
It's just a region of space.
Yes, it's a place.
A region of space. Okay, so what's some background on this? Jenny, can you tell me, when did the black hole physics come online?
Well, so one of the really cool things to me is that when I learned about gravity in high school, I learned that it was
We went to the same high school. Not at the same time, because I'm an old fart, but we went to the same it was the Bronx High School of Science.
Bronx High School of Science.
We're both from the Bronx in the house today.
Where I learned that gravity was a force of attraction because objects have mass, but light doesn't have mass. So there's this magical thing that it's actually bending in space and time, which light also moves through space and time and so knows the effects of gravity. So the very first thing was we had to have this idea of general relativity.
General relativity. So that's Albert Einstein, your favorite man?
My favorite.
Yeah.
Yeah.
You guys should know this, that there's an ongoing feud between these two, whereas, of course, Neil's
My
man
Newton friend.
is Newton.
Yeah, Isaac
That's
Newton.
that's
my
his
man.
man.
Yes.
And her man is Einstein. And often it's wonderful to get drunk and watch them fight about who is better.
Isaac Newton discovered the laws of optics, the laws of gravity, and
He also stabbed himself in the eye with a stick to test out the rods and cones.
yeah, just as
Hey, let me just say, doesn't sound like a genius to me.
but he did all of that and decided to invent integral and differential calculus.
It's pretty impressive.
Then he turned 26.
Ooh.
Mic drop.
Oh. All right, Janna, your response?
Well, Einstein said of himself, you know, when I was a student, I was no Einstein. So he was
Okay.
actually
That's a
not
really
a very
great
good
line,
student.
by the way. That's really cool.
All right, let me clear up a couple things. So we needed Einstein to
Yeah.
advance these ideas, but Einstein did not even come up with the idea of a black hole. Actually, we can go farther back in time,
Okay.
to the late 1700s.
Okay.
There's a physicist named John Mitchell.
All right.
John Mitchell. Forgotten. Long forgotten.
He is, because until you said it, I still don't know who he is.
John Mitchell wondered, once the speed of light had been established, he wondered, could a star be so massive that the light cannot escape and that the star turns dark?
Ooh.
And he called them dark stars. So this is the brilliant, even before Einstein and before he had the math tools to do this, he advanced this concept. And oh, by the way, John Mitchell, I have on here in my notes, what I think is fascinating. All his work was forgotten. No one knew about this.
Oh, yeah.
He had to be rediscovered.
Clearly nobody knew. Nobody here knows
Okay,
about him.
okay. There's no picture of him, and he was described by someone. This is fascinating.
Go
This is
ahead.
in England, of having. He was black of complexion.
Oh. Okay. So either he had bubonic plague, or he was a black man.
Okay. Is bubonic plague Black Death? Is that right?
That's the Black Death.
That's the Black Death.
That's why they
Yeah.
called it that. 'Cause,
Yeah.
you know, you actually turn black,
Yeah.
which is why it gets such a bad rap.
Is that why? There's no picture of him, so we actually portrayed him in Cosmos, and we had a black actor portraying him. Just put him in there. Didn't even mention anything about it. It was just
How fitting that a black man discovered the black hole.
okay.
Behave yourself.
When we think of black holes, we think of this voracious vacuum cleaner that whichever direction it just eats things up. So is that accurate?
Well, as we have discussed, things can't usually fall directly into a black hole.
Okay.
They have some energy, and so actually they tend to orbit, swirl
Okay.
around the black hole. And this stuff
That doesn't sound like a very good vacuum cleaner if stuff's got to swirl first.
swirl
But it does
first.
sound like an awesome toilet.
Wait,
So cosmic toilet.
okay, so this whole thing that black holes suck, the way
Yeah.
a vacuum cleaner, this is
It's
wrong.
very overblown. If our sun right now were to turn into a black hole, it
With
would
the
be
mass that it currently has,
the mass that it
shrink
currently
it to a
has.
black hole.
Shrink it. Some evil genius comes along, figures out how to shrink it to a black hole. It becomes 6 kilometers across. It's a really tiny little thing. Our orbit would
There's
be.
America. What's 6 kilometers?
I'll tell you what it is. None of my damn business.
It's about 4 miles across.
I've lost
Okay.
miles a long time.
You lost a long time ago.
Yeah,
It's
so
about
it
4
would
miles
fit
across.
inside New York City. You know.
Okay.
Our orbit would be just fine. So we would no more be sucked into a black hole than we are sucked into the sun. There would be very little detectable difference in terms of the Earth's orbit. We'd be perfectly fine. So this is a completely overblown
Wait, we
hysteria.
would rapidly freeze to death.
That would be bad.
Okay, so don't say we'll be fine.
Okay.
Just be
The
clear.
Earth would be fine. The Earth would just keep
As a
right on.
planetary
yeah,
object.
right. As
the
a planetary
rock,
object.
The rock would persist in its orbit. We would be gone. Yeah.
and all life on Earth, but there's life that thrives undersea that absorbs energy from undersea vents, which is leftover heat from the formation of Earth.
Right.
So depending on your age in the audience, I am of that age, we learned that from our biology textbooks that all life on Earth requires sunlight to survive. Take away the sunlight, we'd all die. That's before we had discovered this life forms thriving at the bottom of the ocean. that are a part of what we call extremophiles,
Extremophiles.
life forms that do the backstroke in
Where the sun don't shine.
where the sun don't shine, right? And so, just to be clear,
Yeah.
surface life would rapidly die.
Yeah, you got to get really close to a black hole is the point. Really, really close. This thing's only 6 kilometers across. You got to get within like 20 kilometers of it. I mean, you're right on top of it.
Which I have no intent of doing.
Yeah, and don't
Okay.
do it to the sun either, because that would also end badly.
I'm going to ask that you guys stop speaking in metric terms.
Right. Okay. No, you could. NASA did a research study. They found that you can send astronauts to the sun, provided you visit at night. Just saying. Janna, why? If Einstein invented the framework to understand and even predict black holes, why didn't he predict black holes?
He did not, that's right.
And when he learned about them, why was he in denial of them?
Yeah, so he gets a letter from a friend who's an astronomer who has enlisted in the German infantry as a German infantry soldier during World War I, and he's on the Russian front during the war. And the apocryphal story is that between calculating ballistic trajectories in the war, he's reading the proceeding of the Prussian Academy of Sciences.
Is this Karl Schwarzschild?
As you do, Karl
Karl
Schwarzschild,
Schwarzschild,
in which
okay.
Einstein has published his final description in mathematical terms. You know, he nails it. General relativity, the theory of curved space-time. And Karl Schwarzschild does this little thought experiment. He says, imagine the
This is
entire
while
mass.
people are shooting at him.
While people are shooting
Yes.
at him, yeah. He's, in the trenches, hiding and calculating. And he does this beautiful thought experiment. He says, imagine you crush the entire mass of a star to a point. He doesn't ask how this is possible or how nature could do such an absurd thing. That's not really of interest to him initially. He just says, imagine it. And then he asks of Einstein's equations to reveal to him what the nature of the curved space-time is as a result of that. And he
So
writes
this is a
down...
thought experiment.
It's a thought experiment.
With the math. Very
Yeah,
good.
with the math. And he writes down the first description that has in it an event horizon, a region beyond which not even light can escape. And it has all the descriptions of the space-time around a black hole. Einstein's very impressed by this. He couldn't believe it. 6 months
Right, it's
after
fast.
Einstein publishes his theory. And he thinks this is terrific. He helps him get it published. But Einstein thinks, nature's going to protect us from their formation. After all, how are you possibly going to crush a star to a point? And so he doesn't think that they're going to be real. He thinks they're
He
a
thinks some
mathematical...
new law of nature yet to be discovered is going to save his ass.
Well, there are lots of laws that were there. Like, I can't crush this glass to a point. It's really hard. It resists pressure. There's matter has pressure.
If you were a real housewife, you'd be able to do that.
I mean, it was
Only if it had
sensible.
Chardonnay. It's gotta have Chardonnay.
I wouldn't do that over a glass of water. Exactly. So there was sensible reason to believe that matter would resist being crushed.
Okay. So this is not sensible reason. I would call it a bias. A bias that he had because he didn't think nature would do that. Okay. So now, when did we have our first evidence of a black hole?
Well, we had our first evidence of black holes, I believe, in the 20s, but I don't think we figured it out until the 70s.
So when did we first figure out that we had evidence of a black hole?
In the 1970s.
1970. So this is 50 years, 60 years after Einstein. Okay, so what's this famous bet between Stephen Hawking and not an Einstein?
Kip
what was
Thorne.
It? And Kip Thorne. Remind us who Kip Thorne is?
Kip Thorne is a very brilliant relativist. A lot of his work as a scientist was in the area of curved space-time, Big Bang black holes, wormholes, that sort of thing. He won the Nobel Prize recently, fairly recently, in the past few years, for his work.
2020.
Yep, in discovering or theorizing about the collision of two black holes ringing space-time like a drum. And when it was eventually observed, a project that he was involved in for more than 50 years, he received the Nobel Prize along with his collaborators. And he's also wrote the treatment for Interstellar.
The movie. The movie
movie.
Interstellar.
He was a slacker.
Not only wrote the treatment, he was listed as executive producer of the series. Did you guys see Interstellar? Okay. Wait, who has not seen Interstellar? Okay, security. Could
Notice
you
they did not-
escort them?
Notice they didn't clap.
No, they didn't clap. They didn't clap.
The people who saw it were like, yeah! Like, who has not seen it? I'm okay.
By the way, those who remember it, there's a robot in it that had these sort of funky rectangular legs.
Yeah.
Do you remember the name of that robot? No? Well, there were several, but the lead one, it was called Kip.
It was called Kip.
The robot
After
was
Kip
Kip.
Thorne.
Kip
Right.
Thorne.
Yeah,
That's how you
Kip Thorne.
get your
Yeah.
situation in the
I
situation.
remember that because he told him to turn down the humor, and I was like, I'm done with this movie.
All right, so there was a bet between Stephen Hawking and Kip Thorne
Yeah.
about this, whether or not we actually had the data justified for a black hole. So what was the first black hole?
Well, I know it was a stellar mass black hole, so 10-ish suns with a star friend, and the black hole is slowly eating material from the star.
So the black hole is flaying the star.
Yeah.
Okay.
So they should call them vampire holes. For real.
Yeah. So I remembered, because this swirling material that you began describing earlier can get very hot and start radiating in a form of light that you get when you have very hot gas, such as X-rays.
X-ray.
And so when we first had X-ray telescopes, we started discovering these sources of X-rays there was nothing else obvious happening in that region of space. And one of them was a strong X-ray source in the constellation Cygnus, and so it was sensibly called Cygnus X1. So I remember, I was alive, because that's how old I am, when that was discovered. We were very excited. We read all about it. Is that still to this day a confirmed black hole?
Yeah.
Yeah.
No?
Be like, yeah. Okay, sorry.
But it is worth pointing out that that doesn't mean we could see the black hole. Like, you couldn't resolve the black hole. You were deducing that the object that was emitting this incredibly high energy, you could tell, had a certain amount of mass and was very, very small, and you deduce from that it's a black hole. But all you could see were the X-rays, so you couldn't see the black hole itself. And I think this surprised people to learn that we really didn't see a black hole for many decades
Let me
more.
just understand this, and I'm serious when I'm
Yeah.
asking this. Are you saying that the X-rays were emanating from the black hole? Is that the black hole is spewing out X-rays?
It's emanating
Because-
from around the black
What's
hole.
that?
From around the black hole.
It's this stuff that's
Okay,
trying to
but-
fall into the
okay,
black
so
hole.
now-
Don't you learn anything? They said nothing comes out of a black hole.
And that's my point. So how are you seeing something when nothing can escape it? How are you seeing anything around it? That's what I want to know.
It's because this reputation of black holes sucking up everything is overblown. Things can live very close to the event horizon of a black hole, be very hot, and you do
And
a
what's
lot of work on
happening
this.
in those disks?
Right, so the stuff gets
The stuff is swirling around.
it wants to get into the black hole, but it has some energy, right?
Okay.
And so it can't just fall right in.
Right.
So what nature does is
It has
forms
orbital energy.
It has orbital energy. That's right. It forms these disks, accretion disks.
Okay.
And what happens in the disk is that the gas cozies up with itself. It
Gotcha.
gets really nice and close.
and it gets hot.
It gets hot. It rubs against itself. It gets hot.
Okay.
And this is super exciting for astronomers because how astronomers study the universe is by gathering light.
Right.
And so without that stuff near the black hole, we wouldn't have found
would
them.
not see it.
So
And-
we're
and so
not
it's-
we're not seeing anything from the black hole itself. All we're seeing is what's happening around the black hole.
Yes.
And that excited material that gets all like, hey man, we about to go into a black hole,
You're
man.
about to die.
It's crazy.
Yes.
And then it gets hot and it gets excited, and then we see that as light, and that's how
Light
we know.
of high energy wavelengths.
High
yes.
energy wavelength.
Exactly.
And so it gets
What the hell is wrong with you people? That is amazing.
Wait. So
I just learned something. I don't know about you, but that is amazing.
okay, wait.
That is
so,
amazing!
So what's raising?
We see nothing, and we know everything from seeing nothing.
All right. Okay. Chuck just blew a gasket. We gotta repair Chuck.
This is why I love doing this show. I'm sorry. This is why I do it. That's amazing. Go ahead. I'm sorry.
Okay, Chuck will be in for repairs this weekend. So this friction is the gas spiraling down, losing that energy that it had, and it's got to end up slow enough to drop in.
It's circling the drain.
The drain.
Yeah.
The toilet bowl.
toilet.
Okay. So this friction, you've done this in cold weather, but you can just do it now. rub your hands. It doesn't take much rubbing to feel the temperature of your hands go up. Just do it. You know the result, but just try it. Right?
First clap them, and then do that. And then go heal somebody. First you clap, then you rub.
Yeah.
And now you're healed.
Oh. I told you Chuck needs repairs. All right, so was there a bet and who won it? Who bet on what?
Oh, so okay.
Stephen
so,
Hawking and Kip Thorne.
Kip is the loveliest guy, and he's a straight shooter. He's going to vote for the black hole, and Stephen was a bit of a trickster and had this kind of inimical quality to him.
She's on first name
Oh,
basis
Stephen.
with Stephen Hawking.
Oh,
Okay.
that's so obnoxious. I'm sorry.
Yes.
Hawking was a bit of a trickster, and so he bet against black holes, even though so much of his life had been devoted to understanding them. I think he also suspected that they were observing a black hole, but he just wanted to, he wanted to bet the, I don't know,
Be
the
the antagonist.
opposition, be the antagonist, be the devil's advocate. So yes, he bet against Kip, but he did capitulate pretty early on. And I think the story is he broke into Kip's office at Caltech or some such.
Wait, Stephen Hawking did this?
Yeah.
What point in his life was...
That's a detail left out of the story.
I'm just trying to
let
figure-
that one go.
I'm just saying.
We'll let that one go. Okay.
Okay.
So he rappelled down the building.
I mean, I would believe it, because I would leave it up to Stephen Hawking to figure out a way to rappel down a building,
Yeah, to break into Kip's office, yeah.
Okay. And so, Sam, what happened when he broke into the office?
Well, I think he left him a note conceding the bet.
Okay.
Yeah.
Okay, so that's odd for him to be anti-black hole because of his intellect, we know so much about black holes. So one of them is like black holes are not forever.
Yeah.
So what do black holes do when left to their own devices?
Well, okay, so this is a very subtle issue because Chuck already raised it. The black hole lets nothing from the inside out again. But Hawking figured out this very clever way. The black hole could kind of steal energy from empty space. And I don't think you want me to get into this whole thing because this is a whole big thing. But there's this possibility that empty space sort of, has this frothing quantum foam that's sort of...
we got into the quantum.
And it is only when you introduce the quantum that this happens, only then. And he figured out a way that the black hole could steal a little from the empty
what
space.
What you're saying is Newton gravity, Einstein gravity alone doesn't get you this result.
Does not.
He has to bring in quantum physics.
Absolutely, yeah.
Which is the physics of the small.
Yeah.
To describe something that's going on in the physics of the large.
And for
Yes.
you children out there, sometimes when Newton gravity really loves Einstein gravity, they get together and they make a quantum.
All right. So is this when we hear that black holes evaporate?
So what happens is the black hole ultimately evaporates. It actually gets less massive, and it exposes something in the vacuum that has to radiate away. So it doesn't come from inside the black hole, but it's in tandem with this quantum process. But what it looks like from afar is it looks like the black hole is evaporating. It is emitting particles at a hot temperature, and it is getting smaller in the process.
When I first learned this, you know what freaked me out? And maybe it'll blow another gasket for Chuck. When I first learned this, it was like, wait a minute. It is spontaneously creating particles out of the gravitational field outside of the event horizon. Outside of the event horizon. So the energy there spontaneously becomes matter. The matter escapes, and the mass of the black hole drops. So what's inside the event horizon loses mass to stuff that's happening outside the event horizon.
All right, I gotta go smoke some weed. I'll be right back.
That's exactly right. It essentially absorbs what we would consider to be a negative energy particle in favor of emitting a positive energy particle. You could say something like negative energies don't exist, but because of the relativity of space and time inside the black hole, you don't think it's a negative energy, you think it's a negative momentum. And so it's completely consistent with the laws of physics.
I'm leaving with Chuck right now.
Yo, that is dope. What you just described is what Harry Potter would call magic.
Yeah.
So where did the term black hole come from?
Oh, so that's a great story because Schwarzschild didn't call it a black hole. Einstein didn't call it a black hole. It was 1967, I believe, and the great John Wheeler, who was the kind of granddaddy of all of relativity in America.
And a student of
He trained Kip
Einstein.
Thorne. Yeah, a student of Einstein's, and he trained Kip Thorne and Richard Feynman and all of these great people. He was on stage near Columbia, like above Tom's Diner, you know, from Seinfeld, swear to you, and giving a lecture. It wasn't Tom's Diner, I don't believe, in the 1967, and he kept saying the end state of catastrophic gravitational collapse over and over again, and apparently from the back row, somebody shouted, "How about black hole?" And he just took it and foisted it on all of us, and one day he wrote something to the effect like the Cheshire Cat, the star fades from view. One leaves behind only its smile, the other leaves behind only the black hole. I butchered that a little bit, but it's something
Okay,
like that.
wow.
And with that usage,
I
it was
just feel
on
bad
us.
for the guy who yelled it out. Because nobody will never know who he is.
Oh, right.
And he came up with the actual name.
All right, Jenny, you focus on supermassive black holes. And, you know, we bandy about the word super so often that it almost loses meaning. I'd like you to sort of give it strength and presence once again. So what's a supermassive black hole? What's an ordinary black hole? Is there a mini black hole? What is the mass range, and where do we find these beasts?
Yeah, so usually when we say supermassive, we're thinking about million suns. That's our own black hole at the center of the Milky Way.
So we say a million suns, you mean take the mass of a million of our suns and cram it into one object to make a black hole. A million.
A million.
And by the way, if the sun were hollow, you could pour a million Earths into it.
So a million.
Million.
A million is what a supermassive black hole is.
Correct. Okay.
Right.
The low end.
What?
The low end.
Yeah.
They can be a trillion.
Yeah, so the friend we talked about earlier, where we saw the base of the jet, M87, we know we've seen a picture of its event horizon. That's a billion suns. So that's
Oh,
some
you got to say it. Billion.
billion.
Carl Sagan like.
You can put your chin out. Everybody together. Together. On three. 1, 2, 3.
Billion.
See, that's how you do that.
Yeah.
Pretty cool. That was
That's how you do that. Okay. So go on.
Right. So when I was a kid, we also had the SIG X1s of the world. These are like the mass of the sun, but a bit bigger, so maybe 10 suns. Now, LIGO, we've seen black holes, or we've heard black holes
LIGO
merging.
is the abbreviation of the telescope, the gravity telescope that Kip Thorne pioneered, laser interferometer gravitational wave observatory. Okay? So go on.
And they forget, where's the wave? See, every time y'all say that, I'm like, there's no W. But never mind. Go ahead.
Like,
They
Astronomers
hyphened it.
love their acronyms. Don't let real
okay,
words
so
get in
you
the
want
way.
to go LIGWO. Is that what you want to say? All right,
Exactly.
fine.
Go ahead.
So for all time, it was 10 suns and then a million suns. And one of the amazing things for me as an astronomer that LIGO has taught us is that it's actually, these stellar mass black holes go all the way up to 100 suns at least. But that still leaves a big space between 100 and 100,000 or a million, and we just have no idea. We just don't know.
Okay, so we don't even know what mechanism could create such an object.
Well, so with the 10-ish sun black holes, we
That's
actually...
just a dead, fat star.
That is the death of
We
a
got that.
star,
We
yes.
got that.
And then these things up to 100, they seem to be probably the mergers of
Those.
those.
Okay.
Right?
Because we don't know
we
how
see
to-
them merging.
Chuck, you see what she did there? It's like, we don't really know how to make those, so let's add the others together, and that's how you get that.
But LIGO has detected 30 and 30 or 60 and 30 merging to the 100 range.
I get that, but we don't know how to make those, so you just staple together the ones that are 10 solar mass. Is that what you're doing?
Well, not with the supermasses.
Okay.
Not with a staple gun.
You
And
guys are witnessing your first science fight.
like nerd fight. All right. So I just admit we don't know what could make a 30 to 100 solar mass black hole.
No, 30 to 100 you can, but a million we don't know
A
how.
million, we have no idea.
But you haven't detected a million yet.
Yeah, like the supermassives at the center of our
Our
galaxy,
own
4
Milky Way is
million.
1 million.
4
Yeah,
million.
4 million.
4 million.
3 point, yes.
4 million, okay.
Yeah.
And the one you mentioned, M87, is
When we come
6.5
back,
billion.
we will resurrect this argument about how massive the black holes are and what in the universe is making them.
Not that size matters.
On StarTalk. We're back for segment 2 at the Keswick Theater, Philadelphia. All right. I got with me Janna Levin, black hole extraordinaire expert, and Jenny Greene, a professor at Princeton University. And we have Chuck Nice. Okay. So in this segment, we want to spend a little more time on detecting the undetectable. And of course, our friend, the one with black complexion, gave a first indication, John Mitchell, of how you might detect it. And that was if a star is dark, and
It will get pulled over by the star police in a second. Do you know why I stopped you? I was not doing faster than the speed of light. That would be impossible.
But we clocked you at 1.5 the speed of light. The speed of light, it's not just a good idea, it's the law. Yeah. So he's supposed, because by then we knew that there were stars that were double. There were double stars.
Right.
More than half the stars you see in the night sky come in at least pairs, and in some cases triples, and even entire clusters. So the isolated star is not even all that common. And the only, I would say, single correct science out of all 30 Star Wars movies was in the first Star Wars 1, which I think they call Star Wars Part 4.
That's right.
Where they show Luke was at the sand planet, and he comes out, and there's a double sunset on the horizon.
Yeah.
And I said, somebody finally did this. And so more power to the people who thought that up.
That's the only thing they got right.
That's the only thing they got right in the entire series. Just thought I'd put that out there. You want to fight, meet me outside. We'll after school. So what he said, so if you just see a star doing loop-de-loops and you don't otherwise see anything there, then something dark has gravity and is tugging on it. So Jenny, pick us up from there. All right. Now we left off when we began with this jets and the thing and all this stuff, and Chuck blew a gasket here in that we still can't see black holes. We got an hour-and-a-half show on black holes, and we still can't see them. So what are the clever ways that ingenious astrophysicists have come up with to detect them?
Right, so this is why I'm on Team Newton, because almost all the ways that we find black holes actually don't even need general relativity. It's just Newton's laws, right?
Like I said, Janna.
I'm going to be the one waiting for you outside.
Right, so the star friend of Sig X1, we can watch it going around Sig X1, and we can figure out there must be a really dense object there. Just like planets going around the sun, we can figure out the mass of the black hole. And in fact, we can do the same for the black hole at the center of our own galaxy, Sagittarius star, and
So there's a black hole. So the Milky Way has its own black hole.
we have our own supermassive black hole. We
Supermassive
have
black-
lots and lots of stellar mass black holes.
And we agreed that's 4 million times.
4 million
And
suns.
the thing about black holes is that they're spatially small. So that's less than 20 times the width of the sun, but it's 4 million times the mass.
The mass.
So picture the sun on the sky, don't stare at the sun, but like picture the sun in the sky. Imagine just, 20 times across, and this thing
And then
is
cram a million suns.
4 million.
4 million suns.
And then
into
push
that
it,
space.
Yeah, and then push it 26,000 light years away, and it's like a tiny, teeny little thing on the sky. So it's about as big on the sky as people liken it to a piece of fruit on the moon. So it's really tiny, and that's why black holes are so challenging, because despite their heft, they're spatially small.
So
Okay. Small and hefty.
All right, so we have this range.
There are many jokes I'm not doing right.
All right. I'm of the age where black holes in the centers of galaxies was a new idea. We found them in one galaxy and then another random other galaxy. And as we do in my field, if you find it in this galaxy and that galaxy, then all galaxies must have it. That was the driving presumption. And sure enough, when Hubble came online, it had good views down in the centers of galaxies, and bada bing. We have yet to find a galaxy that does not have a supermassive black hole. Is that correct? I guess not. Okay.
That's not correct.
Sorry. Meet me outside. We'll settle this in the parking lot. No.
Great.
Big
Okay,
galaxies like our Milky Way or M87.
Yes.
So far as we know, they all or most.
Isn't
But
that-
so far as
well,
we know,
I say-
all.
Wait, here's the real question. Have we found galaxies where there are not supermassive
Big
black
galaxies.
holes? Yes, yeah.
Red-blooded American galaxies.
Yeah, like the kind of galaxy you would put in the back of a cosmic pickup truck.
Yeah, a pickup truck with a gun rack.
That's right.
You got one of those?
We have smaller galaxies that don't have black holes.
Okay.
Is it possible they were?
We have not yet asked for their passport, so we can try that.
All right.
Okay, I got you.
All right, so now this galaxy, one of the most massive galaxies in our catalogs, is in the Virgo cluster, supercluster of galaxies, because galaxies cluster the way stars cluster.
They're very cliquish.
That's the universe just doing its thing with gravity. So we have the Virgo supercluster, has thousands of galaxies. The most massive galaxy in that is in the Messier catalog. Messier was a French astronomer in the 1700s.
And an awesome hockey player.
He wanted to make a catalog of fuzzy objects in the night sky so that you don't confuse them for comets that you might be trying to discover.
That's pretty cool, man.
So it's called the Messier catalog. And it's really the catalog of not comets. But it turned out to be a catalog of the most famous fuzzy objects in the night sky, including Messier 87, which is this supermassive galaxy. It's far enough away, it's just a smudge of light, but it's got trillions of stars. So we, the astronomical community, recently published a photograph of that black hole. Tell me about it.
We can actually see light swirling around the event horizon because astronomers are incredible at working together to build these pictures. And as Janna said, it's a piece of fruit on the moon.
In terms of angular
In terms
size.
of how big it is in the sky.
So I've heard there's something called the Event Horizon Telescope. So that lets you think there's like one telescope sitting somewhere looking for black holes. But what is it actually?
So it's a network of telescopes. And what's important for getting a tiny, tiny picture is that you put your telescopes as far apart as possible so that you can get this really, really high angular resolution.
So you're not getting different sets of data in principle. You're getting one coherent set of data as though the telescope were as wide as the diameter of the Earth.
Basically. Although you have to work really hard to make the data coherent.
Taking the same
It's the
picture.
same, a bunch of cameras taking the same picture.
Yes.
And you get the resolution of something as wide as Earth, as though your telescope
As
were
though
that
your
size.
telescope were that size. But in fact, you have all of these different telescopes you're
And you
coordinating.
have to combine them.
They each have detectors that somebody had to build and commission.
How many total astronomers are involved in this, approximately?
300?
300
I don't know
all
the
around
number.
the world?
Is it bigger than that?
I looked at a list of the collaborators, and I'm like, what? Because in it are
He's like, I cannot believe they let George on here.
there are countries that historically and even today were at war with one another. Yet the scientists are collaborating.
Yeah.
Can you comment on that?
Oh, yeah, I
That
absolutely.
deserves applause.
Yeah.
I don't know who wanted to applaud.
Yeah.
Somebody
Yeah.
started applauding, but yes, that deserves applause because, quite frankly, only these guys can absolutely hate each other, but love science so much that they will continue to work together. And that should be a model for the rest of us to follow.
Right. The geopolitics of the world.
It should be.
So the Nobel Prize in Physics, which includes prizes for astronomy, can only be awarded to 3 people or less. And there has been sort of a discussion, I don't know how seriously it was taken, that the Nobel Peace Prize should be given to major scientific collaborations. Because they are working both across things like the Large Hadron Collider, the James Webb Space Telescope, the Event Horizon Telescope. These are examples of what human beings can do if we put our minds to it.
As a model for geopolitics.
Yeah,
Yeah, interesting.
absolutely.
Here, here.
So you'd simply open up the Peace Prize to not only the usual things that might earn it, but then the collaborations that transcend governments.
There
All
are
right, enough of your
demonstrations of
commercial.
it.
Okay.
We got the message.
All right. So I want to get back to this jet we first started talking about.
Yeah.
So we get this disk, accretion disk, which is officially called around a black hole. By the way, when I think of accretion disk, I kind of think of a middle accretion disk around my equator. The middle-aged man accretion disk.
Why? Are you eating accretions?
No, just so okay. We got through that and we rubbed our hands and we figured this out. But now we have jets. So tell me about jets.
Oh, yeah.
I'll talk about, do you want to talk about jets?
Go for it.
No, you go for it.
I will tell you this about jets.
I
Roger,
like she leaned in on that one.
Yeah.
Grabbed the drink.
And before you do, let me tell you about jets. When you're a jet all the way. From your first cigarette to your last dying day.
So I have these accretion disks. How do we get a jet out of that?
well, I guess the exciting and beautiful thing is we don't really know.
Oh, okay.
It's got
So-
something to do with the black hole. The black hole's got a lot of energy. There are these particles that are accelerated. We think we're getting the energy from the black hole to power the jet. But I'll tell you what, when I go to meetings about black holes and accretion, the jet session is when I leave to go see the European town that I'm visiting.
That was a big confession. That was like a public
That was the most
confession.
elegant diss I've ever heard.
That was cold-blooded.
Oh,
Dad.
For
Can I
30
embellish
years,
it?
we've been talking about how to
Yeah.
accelerate jets, and we just don't know.
But I do think that the irony is that what the black hole is basically doing is it's acting kind of like an electromagnetic battery. So there are these magnetic fields that are threaded through the accretion disks that the black hole can't do on its own. It needs that stuff around it. And then the churning of the space-time due to the black hole actually basically creates a gigantic battery which starts to power these jets. So these jets are electromagnetically powered. And so black holes go from being the darkest phenomena conceivable, as we discussed in the beginning, to the largest sources
Engine.
of electromagnetic power in the universe that we can see at the edge of the universe.
So is this an overload of this electromagnetic battery that it just can't contain all the energy that is being generated inside this accretion disk, and all of a sudden
We
it's just
accelerate
like,
the particles
it accelerates
out.
the particles,
Yeah.
they get excited, and they're just like, I'm out of here!
Yeah, yeah.
And that's it?
Well, literally, it's churning up the magnetic fields, and then the magnetic fields are literally like wires in a circuit, and the charges are currents.
Following them out like
They're
currents.
currents flying out on the circuit.
This is why science is awesome!
okay. All right.
That's the second thing I learned tonight. That's amazing!
It is amazing.
Chuck just blew a third gasket on that. So Jenny, tell me about your work with the James Webb Space Telescope. We've all been enchanted and stupefied by the beauty and majesty and its access to previously untouchable parts of the universe.
So it's really life-changing. I would say it's like a once-in-a-career experience it's been for me to see the James Webb
Okay,
data.
cool. All right.
So as we said there are stellarish mass black holes and there are supermassive black holes, and then we don't know how to make the supermassive black holes, but we figure they must have started out smaller, somewhere in this intermediate mass black hole regime where we can't find any. But for my whole career, I've been saying if we can find these intermediate mass black holes, we can understand how supermassive black holes form. And I've been saying we're never going to find them back near the Big Bang early in the universe because we just don't have the telescopes. So let's look for them nearby. And that's been most of my career. And now all of a sudden, we put this, 6-meter gold-plated thing into space, and we are, honest to God, we're finding the baby black holes.
You're finding baby black
Baby
holes?
black holes?
Yeah.
Oh my God, are they cute?
They are so cute.
Are they like Grogu? Are they like little baby Yodas?
I don't know how you would feel if you saw the spectra, but when I see it, I'm like, oh, it's so
Well, you're
cute.
reacting not to a photo of the black hole, you're reacting to a spectrum of the energy emitted in the vicinity of the black
Right,
hole.
it's the accretion disk again. Yeah.
And you just are touched, it warms your...
It looks like the data
I
that
gotta tell you, kind of sounds like you're being catfished.
I really hope not.
Yeah, so these black holes, you say they're baby black holes, that implies they're young, but are they actually young or are they just small?
Ooh, good
Well,
question.
so
Look
all-
at Neil.
All the black holes are young because we're seeing them,
As they
just
were.
a few million years after the Big Bang, right? Because James
Okay,
Webb,
so everything is that age.
everything is young. Yes, they're all adolescents back then.
Oh, that's kind of dope.
As we see farther out in space, we look farther back in time.
Right.
So we see things not as they are, but as they once were.
Ooh. Oh, that sounds so romantic. And now I feel like looking back at my life.
All right, so this has stoked your career.
Yeah.
Wow. Okay, so you're still studying them. There's anything you can share with us about it?
Anything new and exciting?
And what is Pandora's cluster? I read about this.
Yeah. So the study that I'm
You
involved
shouldn't
in.
study anything named Pandora.
I'm just
Right.
gonna say.
Yes. Right.
That's a bad
I'm
omen
gonna
right
say
there.
that's really good
Maybe.
advice he just gave you.
All right.
You already covered galaxy
Jenny.
clusters.
Yes.
Right? Well, this is a galaxy cluster. It's got 1,000 galaxies in it or something, and that means it sits in a really big dark matter halo. And we've already talked about how space-time can bend light, right? So
Wait, pause. What's dark matter?
So dark matter is a form of matter that does not interact with light. It's that simple.
Okay, wrong answer. What is dark matter?
we don't know. We
Dark-
don't know
we
what
don't
dark
know.
They
Is that
do.
what I'm saying?
We walked into that one,
It's
yes,
not,
thank you.
It's not only that we don't know, we have no freaking idea. Okay.
I would say we have a little bit of an idea because we do know that it acts like matter and we do know it doesn't interact with light and we know that there are things like neutrinos which exist which are technically dark matter. No question. And by the way, it probably shouldn't be called dark. It should be called invisible. Like if I had a handful of it, it's not that it would be dark. It would literally be invisible. So
Okay.
it doesn't scatter light. It doesn't absorb light. Light goes right through it. So we don't know what this dark matter that makes up the 20-some% of
But you
the
don't even
energy
know if it's
vector of the
matter.
universe.
So what you really, but you know it has gravity. So you should call it invisible gravity.
Well, we know it acts like matter in its pressure, energy, its equation of state of
Okay,
matter.
all right.
Looks like regular matter in that sense.
Okay.
So it's implicated as particles.
All right.
Whereas dark energy is not particulate, presumably. And also we don't know what that is either. And also it's not dark, it's also invisible.
This sounds like a case for a science Angela Lansbury.
So you've got this cluster in the middle of a dark matter halo.
So we have James Webb, already an incredibly powerful telescope.
Yes.
But we use the power of gravitational lensing to make it even more powerful. So because this invisible mass is sitting between us and the very early universe, the galaxies way back, 500 million years after
So
the universe
just much
started.
farther back in time than the cluster you're studying.
That's right. The
Okay.
cluster is basically right here.
Okay.
But what we're using it for its mass. And it
As
is
like a lens.
It's lensing these galaxies. And so we can see even smaller and even further back in time because we're using the power of
You are
gravitational
exploiting
lensing. We are exploiting
the
this cluster.
magnifying effects of Einstein's general relativity in the distortion in the fabric of space and time to see where even that telescope, the James Webb, would not have seen without that cluster. Is that correct?
Correct. So my colleague, Ivo Labe, who runs this survey, he found, so remember James Webb was built had to have infrared vision, because as the universe expands, the light gets stretched out. And so by the time it reaches our telescope, it's redder than when it left its galaxy. So we need these infrared goggles.
So just to be clear, because I don't know that everyone fully appreciates that design feature of the James Webb Space Telescope. Because I remember, I'm old enough to remember when we were speccing what it should do for us, like no other telescope before it, and we said, we want to see galaxies being born. Well, what kind of light are they emitting? Well, they're emitting like ultraviolet. Well, how are we going to see it today? Well, over that time, it's going to become infrared. So we built a telescope to detect the infrared that used to be ultraviolet at the time the galaxies were emitted.
Thank God we don't have that technology for actual children.
So it's an extraordinary achievement in our understanding of the universe and the power of our technologies to make that happen. Just a shout out to the engineers that empower what we do as scientists. Yes. Okay. So continue, please.
So my colleague Ivo, he's looking for baby galaxies. We have this lens, this magnification to help us out. And what he finds are things that are way redder than any galaxies we expect to see. And what he thinks he's found are basically universe-breaking galaxies. They seem to be way bigger, like the size of the Milky Way already. And no one thinks there was enough time to make those galaxies yet. How did you make all of those stars so quickly?
Because it takes a certain amount of time for a galaxy to form.
And we don't have that kind of time.
It's too close to the
Yes.
actual singularity
That's
that
right.
we're talking about
That's
to begin with. So there's an incongruency in the time itself.
So these galaxies shouldn't exist in our current understanding of the early universe.
Yeah, so it turns
what'd you do
out,
about that?
it turns out, everybody knew at the time, well, the other way.
Everybody knew.
Now y'all know how I feel all the time.
Okay.
What's the other way you can make this very red thing that seems very powerful? It seems like it's powered by lots and lots of stars, but as we've already established.
Oh, we have objects in the universe called quasars.
Correct.
Which can generate intense energy it's a regular galaxy, but the center of it can generate intense energy, and we think some of that intensity is because it's aiming stuff at us. Is this where you guys are landing?
Well, it's probably just a regular accretion disk, but it can make a lot more light than stars. And so now
Because it hasn't collapsed into a black hole.
there's a black hole in the middle.
In the middle.
And it's our hands
And
rubbing
it's-
together, that accretion disk. So we think, in fact, instead of universe-breaking galaxies, he actually found a bunch of accreting black holes early on.
Okay.
Oh.
All right, so...
Wait, y'all get this? That was some deep stuff, man. So come on, no, because I'm serious. That I just got what you're saying. Is like, basically, you look back, you thought you found this galaxy that was old enough to be a galaxy, but it's too close to the singularity to
Yes.
actually be a galaxy.
Yeah.
But really what you found were a bunch of black holes just hanging out like, yo, what you up to, man?
I know, it's just sitting there.
Want to have a little something, man? Like, you know,
That's
and
right.
so it's all these black holes that have gathered, and because we can't see them, what we're really seeing is all the energy that all these black holes are giving off. So it's not these
Total
super
galaxy.
old galaxies.
Right.
It's a bunch of young-ass black holes.
Young-ass
Right,
black
Like,
right.
holes.
yo!
Right.
And that's what it is.
You got it.
Science!
Right. Okay. But Chuck, I want to take a slightly different view of this.
Okay.
Jenny,
Neil.
James Webb discovers 5 galaxies that don't fit our understanding of the universe. So rather than allow our understanding of the universe to break, you invented some explanation for it so we can continue to think that we understand the early universe.
Oh, he just killed everything I said.
Isn't that what just happened here?
Well, but the thing is that we
Well,
got
but. Okay. What?
we got spectra.
Oh, okay.
Yeah. So
Yeah, black holes!
black holes.
All right, when we come back, we are going to dive into the belly of the beast and find out what the laws of physics tell us of what could be going on inside a black hole, and whether any of that physics and understanding of the space-time continuum would even allow wormholes. When StarTalk Live at the Keswick continues. And now, the third and final segment of StarTalk Live at the Keswick Theater. Let's do this. I am with my comedic co-host, Chuck Nice.
Hey, hey.
All right, and we've got Jenny Greene from Princeton. And we've got Janna Levin from Barnard and Columbia. Two of the three of them are experts in black holes.
Yes.
So we're in this segment, we're going to talk about what's inside a black hole. And is there time travel? Is that possible? Let's go places that telescopes have never been. Let's go ahead and do that. So, Janna, in your recent book, The Black Hole Survival Guide.
Ooh.
I know, right?
Yeah.
When do you plan to?
Yeah, what I'm saying, you clearly build a spaceship.
Are you going somewhere?
Yeah. I'm not going to do the spoiler alert, but yeah.
But you take the reader.
It doesn't end well, as we've described.
You take the reader on a journey towards a black hole. You cross the event horizon and take it into the depths of oblivion. And she's laughing. This is sinister
I know.
here.
It's a little sinister.
I'm a little worried about this right here. Right here.
I'm feeling a little punchy.
Right here. All right. So tell us about that.
Well, we were discussing how if you cross a big enough black hole, which most black holes are big enough for human beings, that when you cross it, it's actually quite undramatic. You really don't notice much happening. There's literally a principle called no drama, which is the idea that there shouldn't be anything special happening at the event horizon. So if you did not know everything about black holes and you simply saw this shadow cast on the sky, like maybe there's a whole bright galaxy behind it and you can just see the shadow of the black hole, and you went and you approached, you would enter the event horizon and maybe not even know you had done so. But then terrible things begin to happen.
Oh.
So your book
sounds very much like Thanksgiving dinner.
Right. But, so, Janna, your book is mistitled because you call it the Survival Guide.
Yeah.
But it's really your recipe for death.
Yeah, it is definitely ill-advised to actually cross the event horizon because it is a guaranteed death experience.
Because you're not coming back.
You're definitely not coming back.
And we all love...
Okay, here's a subtle way you might come back.
Okay.
Oh, there's a way back.
There's a tiny way back. So we talked about Hawking. And people have been arguing about this whole Hawking thing for a long time. So if black holes evaporate, eventually the black hole disappears. And this event horizon, which is like this curtain blocking everything that happens inside the black hole, separating it forever from us outside. You're in, you're never coming out. No information comes out. When the black hole evaporates, it's like the curtain's been yanked up. And where did all that stuff go? And so this has been a really hotly debated topic for a long time. And you might say, it just disappeared, but physics doesn't allow that sort of thing. That breaks physics. And so people have been arguing, well, maybe the information actually does come out of the black hole.
Information that was previously lost by having fallen into it.
And the information could be that it's Neil deGrasse Tyson, and it's all your quantum numbers, and it's all the way you're organized. It's in your entire life history. And if you fell into the black hole, we would never, ever be able to get that information out, except through this really subtle, magical thing Hawking discovered of the radiation. So maybe if I wait outside the black hole long enough and I collect every detail of that information that came out, I could reconstruct you from that quantum information.
Oh, it's like every Star Trek transporter episode.
Yeah. Okay. All right. So
I'd put you back together again.
So tell me about if you actually greet the singularity at the bottom of the black hole, then you should at some point have become spaghettified.
Yeah. Well, you're the king of the spaghettification story.
I
mean, you tell it better than anybody. I mean, I'm not going to Neil deGrasse Tyson you.
Is it my turn now?
Yeah, it's your turn.
Should I give my account of spaghettification? All right. You guys seated? Okay. So what happens is, as I stand here on Earth, you don't feel this, but you can calculate that because my feet are closer to the center of gravity of the Earth than my head is, that Earth is actually pulling on my feet more strongly than it is at the top of my head, because my feet are closer. You don't feel that difference. You can calculate it is insignificant, and all the molecular structure of my body resists that on a level that you don't even notice. Well, that's because I'm here 6 feet 2, and the radius of the Earth is 4,000 miles, and 6 feet relative to
6,000 kilometers.
All right, but now watch. We get one of Janna's small black holes, and I'm falling towards the singularity. Now my height becomes significant relative to the distance that I have left to fall. So the gravity at my feet gets stronger and stronger and stronger relative to the gravity at my head. And I begin to stretch. Now initially, a stretch, who doesn't like a good stretch?
Oh, so refreshing.
And then until you realize this is not stopping, and these are called tidal forces.
Yes.
It's the stretching force of gravity's difference from one side of you to the other.
It's when the black hole gets medieval on your ass.
That's I hadn't thought of it that way. That is totally one of those racks, you know, where they try to. Yeah, the medieval times always trying to rip you apart somehow.
Somehow.
Drawn and quartered.
Yes.
Okay, so you're falling in, you feel the stretching, and then you realize this is not stopping and it's no longer comfortable. And it reaches a point where the tidal forces exceed the molecular binding forces of your flesh. And you split. You split, likely at the base of your spine. Now you are two parts falling towards the singularity. And they feel the tidal force of the black hole. And so those two parts stretch. You will probably still be alive at this point because you have important organs but not vital organs below your waist.
Right.
So
It's like when you see that zebra getting eaten by the lions, and it's looking down at them like, I can't believe y'all eating me, man. That's messed up, man. I can't believe that y'all are eating me.
So you bifurcate first into two parts, then your bottom half and upper half bifurcate again. And that next one will probably sever you at your neck. And you might survive that a little. The experiments during the French Revolution where they're just chopping heads, you might as well participate in a science experiment while they're doing this.
Exactly.
That the eyes connect directly to the brain, don't require the rest of your body, right?
He saw the whole thing coming.
Okay. Do all French people smoke in your imitation?
Of course we do.
Okay.
Especially when we are at the beheading.
So you go from 2 to 4 to 8 to 16, 32, and you bifurcate all the way down until even the molecules that previously held you together, the tidal forces end up splitting those. And you become this stream of atoms descending to this cosmic abyss. And that's not even the worst part. As you're falling in, you are being funneled down to a narrower and narrower volume of space-time. So you're not only getting stretched head to toe, you're being extruded through the fabric of space-time like toothpaste through a tube. When you step back and look at this, basically, there's no other way to describe it, you have been spaghettified.
And the whole time that is happening, you are hearing, when the moon hits your eye.
All right, so suppose you survive your trip through the event horizon, okay? What's this stuff? You can see the back of your head? What is that?
Oh, well, that can
The
actually...
cool optical effects.
Yeah,
What's
that
going on?
that can even happen just outside the event horizon, actually. There's a point where if you were shining light on your face and the light was reflected off, or actually shining light in the back of your head, it was reflected off the back of your head, it could travel all the way around the black hole and you could see it. Because even the
You
light...
see the back of your
The
head in front
light
of your
gets
head.
caught in orbit just like the International Space Station orbits the Earth. You can put light in orbit around a black hole if you get really
So
close.
it's basically the photons are orbiting
Yeah.
around so that
Yeah.
your eyes are receiving
Yeah.
the same information from the back of your head
Yeah.
that you are looking at so
Yeah.
you can see the own back of your
Yeah.
head. That is so dope. I'm sorry.
But what is interesting is inside a black hole, there's this whole black holes are dark and all that lore is completely true from the outside, but black holes can be bright on the inside because the light from the entire galaxy can fall in behind you. And so as you're on your way towards the singularity, the light travels faster than you do, and it can catch up to you, and you can watch the entire history of the galaxy unfold sped up for you.
The future history.
The future history. We could watch the Earth find out what happens with the whole climate change thing. Yeah.
Oh, believe me, we already know.
You can watch all the stars in the galaxy expire, I mean, depending on how long you take to get down there. And so it actually is quite bright for you inside a black hole. It's like all that light gets crushed towards you as you're falling towards the singularity.
All right, so it's
light,
dark in front.
it's dark outside and bright inside.
Right. Because light can't escape, but the light is still in
The
there.
light can fall in.
So the light overtakes you because you're just falling at a rate of gravity, but the light is coming in at the speed of light.
That's right, and it's all crushed together, so you see a very bright white flash of light just as you're approaching the singularity, and it's like, the
Isn't that
light
when
at
you
the end
die,
of a
you see
tunnel.
some light?
Right, it's like a near-death experience, except it's a total death
It's total
experience.
death experience.
Yes.
It's
There's
more,
nothing near death about it.
it's
It's a
more like
total
look,
death
Yeah,
experience.
it's a
it's more like
total
looking
death
into the ark and rays are like, it's
Yeah.
beautiful, and then your face melts.
Right.
All right, so we've gotten this far and on Einstein's gravity. But we know, or at least the equations tell us, that all this matter collapses down to a singularity, which disturbed Einstein. There's got to be something that stops it. So is this the edge of general relativity's relevance in the universe?
I do believe that
Because aren't we dividing by zero there?
Yeah, the singularity is what it really is it's predicting.
For those who don't remember from their math class, you're not supposed to divide by zero. Okay? So we have a condition here
Yeah.
where your equations blow up.
Yeah, you're getting an infinite curvature, infinite gravitational energy density. And I don't think anyone really believes that that's what actually happens.
So you have to abandon general relativity.
I think it's
in
like
that spot.
general relativity is signaling its own failure. And it is saying when you get to those high energy scales, we know that we have to invoke quantum mechanics. Because as you said, quantum is of the very small. So here you're in a very tiny, tiny region of space where the energy is very high. And there's no way you can talk about it without understanding quantum gravity. And we don't understand quantum gravity. So we know that the singularity isn't a declaration of what's true. We know that it's telling us that we need to understand quantum gravity before we'll really know what's going to happen in the center of a
So
black hole.
I have a book
But don't
on...
we have the same problem with the quantum that we do with black holes? Is that we can't see the quantum?
Well, you mean in the center, we can't see the quantum in a conventional human way because of our
Right.
big macro scale, but we've learned to probe the quantum in a very compelling way that we have. It is the most accurate predictions in the history of science we get from quantum mechanics that are confirmed by experiment.
Right.
So it is stunning. It is something we don't really understand very well. It's very elusive, but
It's
our
really spooky,
predictions...
freaky predictions.
It's very spooky, freaky predictions, but the accuracy exceeds the accuracy of any scientific prediction in the history of human culture.
So if you're a betting man, you would say that at the singularity, quantum physics absorbs general relativity.
It's going to rewrite the story, and it might rewrite the story with little things like wormholes. So it might be that
Wormhole.
as you get into, this might be a crazy idea. I actually don't think it's that crazy. But that when you get to the quantum scale inside the black hole, you realize that there are these little wormholes, quantum wormholes, that are negotiating the interior and the exterior of a black hole without traveling inducing faster than the speed of light travel. And in fact, one of the really spooky ideas is that, in fact, the black hole is totally made up of these quantum wormholes. And so it's like, imagine embroidering a circle, and you look like you have this big dark shadow, but when you look closely, you realize it's just these tangles of thread. And so at the quantum level, we might realize that the black hole, its shadow, the event horizon, all of it is really woven out of these quantum wormholes.
Chuck, you got that weed ready?
I'm telling you. Jesus. That's like wild.
Right.
It is wild, and that's how the Hawking radiation would get out.
I got
It's
one
one
for
of the
you.
spooky things
I got one
it's
for
talked
you.
about. Yeah.
You ready?
Yeah.
I ran the numbers on this because large black holes are not on average dense, other than the singularity. Big black holes have slightly different macroscopic properties. Like how should I say? So let me put it another way. If you take the mass of the universe, and then I ask it, how big a black hole would the mass of the universe make? What would be the size of that event horizon? And it's the size of the horizon of the universe that we observe. So is the entire universe a black hole as seen from the outside of our event horizon? And are we simply alive, enjoying the contents of our own black hole?
Well, we better get to enjoying it quick because we all about to be crushed into nothing, that's for sure.
I'm just asking.
Well, I mean, it's an
Is the
intriguing
universe a black
suggestion.
hole?
I would not say the universe is a black hole, but I would say we do have an event horizon as well, cosmologically. So inside the universe, we're looking at the expansion of the universe. And there is a region which we can very well articulate around us, beyond which light will never reach us. It is also an event horizon. So the universe goes dark for us beyond that point. There are things we will never see.
That's everything you said about the black hole.
Yeah, that's right.
Is the universe a black hole?
It's still not a black hole because we're not. The thing about a black hole is it's not just this region of space that you can travel around and paddle and survive forever. Once you cross that event horizon, that singularity is actually a point in your future. So I want to emphasize this. If I look at the black hole from the outside, I think that there's a center to it because it's spatial. I think it's round. I think there's a point in the center. That point might be the singularity. And if you fall in, maybe you could avoid it. But when you're the person falling in, your space and time have rotated so much that that singularity is actually not a point in space for you at all. It's a point in time. And that singularity is in your future. And you can no more avoid it than you can avoid flowing forward in time.
I gotta go. Y'all have a good night. I hope you enjoy the rest of the conversation.
Oh, wait. So you mean this literally, not just figuratively?
Yeah.
I mean
that
it literally.
The black hole is in front of me in space.
From the outside, you think it's a point
but
in
as I
space.
cross the event horizon, the rotation of the coordinate system is such that the center, what I wouldn't want to think of as a position in space that I might sidestep, it's no longer a position in space. It is on my timeline, and I cannot avoid it, and I'm going to get crushed at that singularity.
It is now an inevitability, Mr. Anderson.
Yes.
Exactly.
Damn.
That was a quote from The Matrix, in case you didn't see.
Yes.
My name is Neil. Sorry. We're just geeking out here right now. So, this is spooky stuff.
Yeah, that is spooky
I
stuff.
got another one for you. I have a book on my shelf, co-written by Stephen Hawking. I read it and didn't completely understand it, but I do remember the pages where it said that on the other side of a black hole, an entire other space-time opens up, as though it has birthed in another universe.
Yeah, that's a really profound idea. So what's really going on there? It's the Hawking and Ellis book, right? It's
Yes, Hawking and Ellis.
Very technical,
Very technical.
beautiful book. So what
To
they
me, it was
did,
an ugly book because I didn't understand it. But Janet, it's a beautiful book.
it was painful though. It was painful. So the idea
Oh, I can't
is
wait
really,
to read it.
what they're doing there is you're saying, you know, this is kind of relevant to your question earlier about cosmology. The Big Bang singularity looks a lot like kind of the inverse of a black hole singularity. So instead of everything falling out of the universe, falling, you know,
Into a black hole.
out of the black hole, everything in the Big Bang is coming out of the singularity. And so they were like, well, maybe I should just sew these two things together. And the interesting thing is mathematically, in this very formal technical book, they can prove that the space-times mathematically can be sewn together flawlessly. And that's not a given.
Wow.
Right? And it's beautiful, and you can sew them together. So they said, oh, maybe when you start to go into the singularity, you're actually blown out into a new Big Bang. And that's another beautiful thing, is that the black holes might be small on the outside in the way we've described, but they're much, much bigger on the inside. you
Like
know?
the TARDIS.
Like
It's
the
the
TARDIS,
TARDIS.
yeah.
It's Doctor Who's TARDIS. And they can be as
Yeah.
big as an entire universe on the inside. And that's a beauty of curved space-time, allows you that kind of trickery. So it doesn't mean that we have a prediction that that's what happens. It's just suggestive that the math permits it.
All right, let's get even more freaky before we close this out. So you mentioned wormholes possibly being the fabric of a black hole. But how about the wormholes in the science fiction sense, where I'm over here, but now I walk through a portal, and then I'm over there, as is displayed in the Marvel superhero Doctor Strange, or of course, Rick and Morty, right? Okay.
So much better.
Yeah, okay. So, is there anything that prevents that? Because clearly, if that can exist, it's going to be used in some Einstein theories.
Yeah, so wormholes are, again, a mathematical possibility that we don't understand how they're possible. It might be like black holes before we realized they were real. So we don't understand what source of matter or energy will keep that throat open. They tend to want to collapse. And so we don't know of any form of matter or energy in the actual universe that keeps wormholes open and allows us to
It's got to be like
transmit.
a negative
But they're totally
gravity.
fine.
It's gotta
Right.
be
It's
like
got
a-
to be kind of a negative gravity. We don't know of anything. But look, there's dark matter, dark energy, and we don't know what those are either. So nobody should say we will never discover a form of energy that can keep a wormhole open. But you know, who knows? Maybe it will be related to the dark energy or the dark matter. So it is perfectly fine to attach space-time with these little bridges. That part's completely easy to understand.
Nothing wrong with that. All right, last bit, Janna, before we call this out. In the movie Interstellar, one of the more poignant, stupefying scenes was when the spaceship was orbiting a black hole. I think they call it Gargantua. And there were a black hole that had a planet, and some of the crew went down to the planet, closer to the black hole, because the planet is orbiting the black hole, and they stayed far away. They had completely different timelines.
Yeah.
Tell me about time dilation around a black hole.
Yeah, we actually even see the effect around the Earth. The rate at which literally our clocks tick is slower closer to the Earth than it is further away. So when we communicate with satellites, there's actually the additional effect of the speed of the satellite, which I do believe causes a greater dilation. But we do see that
No, you can run the math. It's actually
You can
less
run the
than the
math.
gravity.
It is
does.
less than the
Yes, less,
gravity?
yeah. Uh-huh.
So it happens, but around a black hole, it's so extreme that this is part of the rotation of space and time that we were just discussing. So if one astronaut stays far from the black hole, they both have perfectly calibrated clocks. The other astronaut travels near in the black hole. And as they do, it's almost as though they're rotating in space-time, such that their clocks are running slower and slower and slower relative to the person further away. When you hit the event horizon, technically you've rotated all the time away. That's why the center of the black hole is in the future time direction and not in the space direction. I'm literally not expecting anyone to understand that.
Okay, yeah. All right.
So,
Like
but wait.
nobody.
Wait,
So,
if
wait,
I
wait,
might-
wait. So what happened, if you didn't see the scene, those 11 of you who didn't see the movie,
Right.
that
Okay,
security
so-
should have removed already.
Right, so
wait,
the astronaut who stays
wait,
far
wait,
away.
So they have astronauts up here when we're down on the planet with them, and 20 minutes goes by, and then they beam, or I forgot how they got back up to the ship.
Right.
And the folks on the ship are
20
gray,
years. Yeah.
and they age 20 years.
Yeah.
And they're like, why didn't you call?
Yeah, they've
You
spent
never
20 years.
called.
And this is a real effect. We literally see the effect even around the Earth. We correct, our phones correct
Right.
for the relativistic time dilation
Wait,
so
wasn't there
that
an
Uber
experiment
can find
though,
us.
where they took atomic clocks and they did exactly that, where one.
Oh, that was 40 years ago.
Yeah.
Yeah.
But no,
Yeah, keep up with the century here.
No, I'm saying, but it's exactly what you're saying. It's proven because there's an actual experiment.
Well, it's also proven because we know that there are subatomic particles which have incredibly short lifetimes. If they're just sitting in your laboratory, they decay in a fraction of a second, but you boost them near the speed of light and they will appear to live for minutes.
Wow.
It's real.
Right, so you were saying your cell phones, so that's the origin of that is the GPS satellites. So the GPS satellites are in a different gravitational field
Right.
from us. So their clocks tick at a different rate because of general relativity. Yet all of our clocks are synchronized and perfect because
We correct for it.
we pre-correct the GPS time for general relativity so that it's correct on Earth time. That's science. All right, so
Yes.
So let me get some closing thoughts. Jenny, what can you tell us just about life, the universe, and everything? Your career being emboldened by JWST.
I'll tell you, my husband always wants to know what's inside a black hole. So now I'm going to go home and tell him I learned what's inside a black hole.
Okay, Janna. close us out.
Closing thoughts. I do think it is quite amazing that black holes are like fundamental particles. They're fundamental to the universe in a way that nothing else is, that we don't really understand. So when the universe was created, it might have made black holes in the same way it made electrons. They might be a fundamental property of the universe. And little
As
quantum
opposed to
black
an exotic
holes.
thing that
Right.
only some
We
telescopes.
think of them as collapsed dead stars, and that is a brilliant way that nature thought of to make black holes, just kill off some stars. But they actually are not dead stars. That's just one vehicle for making them. And we do think that black holes might have been created in the early universe, and they were like as heavy as a little pile of sesame seeds, but they were smaller than a proton. And those quantum black holes would have evaporated away like firecrackers. But they are a very profound and fundamental property of the universe.
Chuck, do you have a...
I do. I have several closing thoughts. But really, I am so proud to see a theater full of people as we discuss these mind-expanding principles, and we talk about things that are so incredible with respect to our being and the fact that we can look up and look out and wonder. And the fact that you are here gives me hope for this entire stupid rock that we are all floating on.
So I'd like to maybe offer some closing thoughts myself, that one of the things we've noticed about the universe is that every time a new telescope comes online, a new telescope, not just that it's brand new and shiny, but that it was conceived to access the universe by looking through a window that previously had not been opened, by looking through a window that we didn't even know was there. At some point, someone has to say, I think there's something on the other side of this window, because I just discovered this new window, and no one's looked through it before. So, we gather funds, we propose, it gets peer-reviewed, and the telescopes get developed, once again, by engineers to empower the science that we have. And what a journey this has been. We are in the centennial decade of the discovery of quantum physics. That was in the 1920s. And you know what actually happened? 97 years ago, Edwin Hubble discovered that our galaxy wasn't the only galaxy in the universe, that the fuzzy things that half of the Messier had found were whole other galaxies. In a sense, island universes, they were poetically referenced as. He was using the biggest telescope available in the day. And so every time we do this, our minds are not only blown, when we put it back together, our minds have actually expanded. And we learn more and more about our place in the universe. So one of the greatest gifts to civilization are the discoveries in astrophysics, because we all look up at night. Yet when the stars call to you, they call to me. I know that maybe you don't become an astrophysicist, but if you walk out at night and it's not cloudy and the moon isn't out, those stars are screaming. And you've experienced this, not in the Northeast. You visit, okay, all right, you go someplace, okay? You know what I'm talking about. The universe calls to you. So I would claim that the study of the universe, opening up these great portals, not only the theoretical portals, but the technological portals to the universe, that there's no greater source of a cosmic perspective than all the new understandings that come down the pipe, that tell us how big the universe is, how old the universe is. And then, in a way, looking back on Earth, it makes Earth all the more precious. In the vastness of the universe, this is the only place we've got. Are we the shepherds we need to be to assure our own survival on our own planet, so that the next generations can be proud of the decisions we've made rather than embarrassed by the decisions we didn't make? So I think, and black holes are just another part of that glorious story. A little more obscure, really fun, good fodder for science fiction storytelling, but I wouldn't have it any other way. And that is a cosmic perspective. Now, I want to show you something. I have in my possession an authentic child's lunchbox. The black hole, the original Disney black hole movie from like 1977, I remember when it was. This is the lunchbox for that movie. Now, I had recently, at the time, because that's how old I am, graduated from high school, and I saw this movie, and it was immediately one of my 10 worst movies of all time. There was no science in it. Even what I knew as a senior in high school, I could have totally tricked out this film. It was an embarrassment. But I have the lunchbox, and so I want to open this lunchbox.
Don't open it! Whatever you do, don't open it!
I'm going to open the lunchbox, and there's a little thermos. So I opened the black hole, and I open the lid, and we heard about the black hole in the center of the Milky Way, but here I have Milky Ways in the center of the black hole. One for each of you. Okay.
I love Milky Ways. Yay. Yay.
That's it. StarTalk at the Keswick Theater, Philadelphia. Thank you. Janna Levin. Jenny Greene. Chuck Nice.